Hello everyone, I'm Xu Yongjun from the Department of Medicine. Today I'll be presenting microfluidic technology for cell manipulation. It's a fascinating interaction of physics and biomedicine. Okay, so let's dive into our topic. What is microfluidics? Microfluidics involves studying and controlling field behavior in microscale channels, enabling precise operations like mixing, separation, and analyze. This precise control allows small volume processes, making it ideal for biomedical diagnostics. It's also central to drug development and plays a critical role in single cell analysis. In this talk, I will introduce key microfluidic manipulation techniques, their principles, and applications. So let's talk about applications first. Microfluidic technologies are transforming the way we approach my biomedical application. In biomedical diagnostics, lab-on-a-chip devices enable rapid testing, such as COVID-19 antigen detection or glucose monitoring. Moving on to drug development, organ-on-a-chip systems mimic human organ functions, reducing reliance of human testing, while high-throughput scanning automates drug testing at a micro scale, speeding up the discovery of new treatments. Finally, in the field of single-cell analysis, microfluidics allows us to isolate and sequence individual cells, which allowing us to studying gene expression in more detailed way. Okay, so today I'm going to talk about four key microfluidic techniques. They are DEP, EP, OT, and AP. First, let's talk about DEP. DEP moves natural or polarizable particles using a non-uniform electric field. Okay, it's important, it's non-uniform. Okay, the force depends on the particles and medium's dielectric properties, guiding particles to regions of strong or weak electric fields. DEP is highly effective for precise particle control, making it ideal for cell concentration and separation. Okay, so let's dive into the principal part. The relative DEP force is generally expressed in the time average manner using the following equation. And for a spherical particle with radius r, the equation is written as the following equation, the following form, where epsilon m is the absolute electrical permittivity of suspending medium, and the k of omega is the Cm factor. Okay, the Cm factor. So as you can see in the PowerPoint, if the real part of Cm factor is more than zero, the DEP force is more than zero too. Okay, so if it's more than zero, the particle moves toward a strong electric field region, experiencing positive DEP. Okay, positive DEP. It's the left part of the picture, PDEP. And on the contrary, if a particle is least polarizable than the surrounding medium, and the real part of Cm factor will be less than zero. It migrates to a weak electric field region, repelled from a strong electric field region by negative DEP. Okay, it's the right part of the picture, NDEP. And DEP is widely used for particle separation, transport, and sorting due to its flexibility and ability to manipulate both conductive and dielectric particles based on their relative polarizability in a non-uniform electric field. Next is EP. Okay, EP relies on a uniform electric field. It's uniform, it's different from DEP, and relies on uniform electric field to move charged particles toward an oppositely charged electrode. And it makes it widely used for separating particles based on charge and size. Okay, charge and size. Next, let's talk about the moving velocity of the particles. The velocity is linear proportional to the strength of the applied DC electric field. Okay, so it can be generally expressed as V equals to mu EP times E. Okay, the mu is the mobility, and as you can see in the picture, the di-layer thickness lambda d and the particle radius rp, they are different situation. If the lambda d is much smaller than rp, its mobility can be expressed as the form I typed on the PowerPoint. And if the lambda d is much more than rp, it has a 2/3 倍数 than the situation I just mentioned above. Okay, so when charged particles suspend in the field moved by EP, they are also subject to two other forces. One is the field friction force, and the other is the electrophoretic retardation force. So this is the EP's principle. And next is OT, optical tweezers. Optical tweezers use tightly forced laser beams to trap and manipulate microscopic particles. The laser gradient force draws particles to the beam's focal points, allowing non-contact and precise control. This technique is highly valuable in biophysics and nanotechnology, but is constrained by limited range, and potential heat damage to samples. Okay, so let's dive into the OT. The focus being introduced, particle motion, has three types of optical force. The first one is scattering force. The second one is absorption force. And the third one is gradient force. The optical scattering and absorption force push a particle along the direction of propagation of a focused laser, balancing with a stock drag in the field. For spherical particle in a laser field with a Gauss's beam profile, the forces are expressed as the first and the second formulas in the PowerPoint. For a non-absorbing dielectric particle, the parameter, the alpha, is positive when the refractive index of the particle is larger than that of the surrounding medium. Then the particle is attracted toward the region of highest laser intensity by the gradient force. On the contrary, when the parameter, the alpha value, is negative, the particle is repelled from the highest intensity region. For alpha more than 0, the gradient force overwhelms the previously mentioned scattering and absorption force in all directions. In this case, suspended particles in a field move along the gradient of laser intensity and stop moving as the laser beam wastes, which is a stable trapping zone. And the last one is AP. AP uses acoustic waves to create pressure gradients that move particles. The direction of movement depends on particle size, density, and compressibility relative to the surrounding medium. This technique is efficient for sorting particles by size, but has limited efficiency for non-scale particles. Okay, so acoustic waves with varying pressure profiles induce the movement of suspended particles relative to a stationary field, exerting an acoustic field on the particles. Such particle migration is defined as AP. Okay, so the acoustic force on the particles is given by the first formula on the PowerPoint. Particles in the influence of an acoustic wave are pushed to either the first, the pressure knots, or the second, pressure anti-knots. The pressure nodes are the location where pressure and density do not vary in a wave field. At the nodes, the acoustic wave forms a zero or minimum pressure. On the contrary, the pressure antinodes represent the locations where pressure and density show the largest variations. The acoustic wave produces a maximum pressure at the nodes. Suspended particles show acoustic wave-based motion depending on the pressure distribution. Then, the direction of particle motion can be explained based on the sign of the U factor defined in the second equation. If the U is positive, the particles move toward the pressure nodes. On the contrary, if U is less than zero, they show migration to the pressure antinodes. So by this way, we can separate different particles by AP. So in conclusion, microfluidics is a powerful tool for precise cell manipulation, with application ranging from diagnostics to drug development. Techniques like EP, DEP, OT, and AP each contribute unique capabilities and face distinct challenges. By improving existing methods and explore hybrid approach, microfluidics holds the potential to biotechnology and medicine. Okay, so this is my reference. Thank you for your attention.